Hello everyone, and in this video, I'm going to be walking through the Clasius Clapeyron equation, and just so I don't embarrass myself mispronouncing this, I will call this the CC equation from here on out. And the way I'm going to do this is by walking through a real-world problem where we're going to need to figure out what the new vapor pressure is of a liquid if we know that liquid's vapor pressure and temperature at a different circumstance. And so this is the best way to really understand why it's important, so we'll get started. And so given that we know water boils at 100 degrees Celsius when we're at 1 atmosphere, just like if you're about to make some pasta, we want to know what pressure the water is going to start to boil at inside of some control volume if the temperature is only 90 degrees Celsius. And so we are given a little hint here that water's heat of vaporization is 40.65 kilojoules per mole, and we are also told that R, the ideal gas constant, is equal to 8.314 joules per mole per Kelvin. And so with all this, we should be able to determine what water's vapor pressure should be at 90 degrees Celsius. Another thing I'm going to make note of here is how when a bunch of scientists and engineers took some liquids and they plotted how those liquids' vapor pressures evolved as a function of temperature, they're noting this thing with an exponential, and they call it an Arrhenius relationship. And so with water and ethanol and all types of other liquids, these people kept noting how these things have similar shapes. And so we can fit these exponential trend lines to these curves, and the constants in front of these trend lines don't really matter. It's really the relationship that was the key insight here. So the key insight that came out of all the work that these people did is that they noted how the P vapor for whatever liquid was proportional to, and that's what alpha means, the exponent of that liquid's heat of vaporization, specifically the negative heat of vaporization of that given liquid, divided by R times the temperature. And so this was what told people the relationship between the temperature and the vaporization pressure of a given liquid. And what makes each liquid unique in all these plots is that each liquid is going to have its own heat of vaporization. That's that molecule's identity, so to speak, in terms of how badly does it want to jump into that vapor phase, because everyone's going to be a little bit unique. But if you're water, and so that's how we're going to be applying this. Is we're sticking with water. And so that's a key thing to make note of here. And so if you do some algebra, what you're going to note is that even though we know that P vaporization is proportional to this exponent, we don't necessarily know what constants are in front of this exponent, but we don't care, because if we take the P vaporization and temperature at two different points, we can divide by that and then cancel out all these constants in here, so we don't even need to care about it. And so the key thing that we arrive at in terms of the CC equation is the following. So the natural log of P1 over P2 is equal to delta H vape of that liquid divided by R, our ideal gas constant, times 1 over T2 minus 1 over T1. And so this is that Clasius Clapeyron relationship that we're going to use to actually solve this problem. And so this, just dissecting our problem statement, is where we're going to find what these values are. So we know that 100 degrees Celsius is going to be T1, and we're going to say that 1 atmosphere is going to be P1, and 90 degrees Celsius is going to be T2. And we can call these whatever we want. You know, we could say 100 was T2 and 1 atm was P2. You're going to get the same results, but for the sake of arbitrarily assigning these values, I'm calling 100 and 1 atmosphere T1 and P1 respectively. And we're also given, sorry, I wrote over it, but we're also given the heat of vaporization of water, and also we're told the ideal gas constant. Now, I want to make very clear here, a huge pitfall I think is made by myself, for instance, is that tracking units and dimensions is very important. And so note how the ideal gas constant is in joules per mole per Kelvin, and our temperature is currently in Celsius, and these are not absolute scales, so we need to convert these temperatures into Kelvin. You do that by adding 273 to whatever the degrees Celsius is. And so T1 here is really equal to the following. So we've got 373 Kelvin for that, and T2 is really equal to 363 Kelvin for that. Now, something else to note here in terms of a dimensional analysis is that because P1 and P2 are in this natural log, their dimensions will cancel out. Consequently, I don't care what units of pressure I use. So I could give this to you in atmospheres, I could give this to you in millimeters of mercury, it doesn't matter, or bar, it doesn't matter. So we can have whatever units for pressure we want as long as you stay consistent. If P1 has units of atmospheres, P2 must have units of atmospheres. You can't say, oh, I'll change P2 to bar because I want to. You have to be consistent so that those dimensions cancel out because you're taking the natural log of it. So for all the math to work out, you need to be consistent with the units or the dimensions of pressure, and then temperature has to be in Kelvin because we are referring to an absolute scale here. And another thing I'm going to make note of is that note how P vaporization is given to us in kilojoules per mole. We need to convert this to joules because joules are what's referred to in our ideal gas constant. So 40.65 kilojoules per mole is really equal to 40,650 joules per mole. And this is that delta H vape for water. And so this guy is what is going to get plugged into right here. Because if we don't do that, if we just plugged in 40.65, we will get inaccurate results. So with the units or the dimensions all figured out, now we can actually begin rearranging the algebra to solve for P2. And I want to make note of here how basically we've got 1, 2, 3, 4 unknowns, or 4 variables here, so I have to give you 3 of them. So I could give you any 3 and then expect you to solve for the 4th one. So someone could just say, hey, if I know P2, solve for T2 for me now. So just how a professor would think about writing this on a test, for instance, is something that does help me too when I'm learning this stuff. But for our intents and purposes and for giving this a practical application, we're going to be solving for P2 in this particular instance. So how are we going to do this is we're going to take the exponent of both sides. And so when we take the exponent, this natural log right here is going to cancel out. So what we're going to have is P1 over P2 is equal to the exponent of the following. So delta H vaporization divided by R times 1 over T2 minus 1 over T1. I'm going to close off our square brackets. And now to actually solve for P2, I'm going to do the following, where I multiply both sides by P2 and then take the inverse of this exponent. So P2, palm rejection is not working. P2 is equal to P1 times exponent. And I'm going to make note that there is a little exponent algebra rule here where if I throw a negative sign right here, negative 1 times heat of vaporization over R, and then multiply this by whatever we had inside there, T2 minus T1, this all works out. So this is equivalent to taking the inverse exponent, but I just put that negative sign right there just for the sake of clarity. This is how we can solve for P2. And P2 will be the vaporization pressure of water at 90 degrees Celsius in our given example, and 90 degrees Celsius would be converted to 363 Kelvin when we actually plug it in here. And so when we do this, and I've done this math, and I'll provide a link to a little Google sheet where you guys can play around with other values, but basically what we have is P2 when temperature was equal to 363 Kelvin is equal to 0.697 atmospheres. And so just think about this for a second, and hopefully it makes more sense. So when we lower the temperature inside of our control volume, the water molecules are not as encouraged to jump into the vapor phase. Consequently, we won't need as high of a pressure in this control volume to allow that to happen. So the higher the pressure, the more external forces there are beating down on those water molecules in that liquid phase to stay in the liquid phase. So we're going to need to lower the pressure inside of this control volume to encourage the water molecules to want to jump into that vapor phase. And so that's how I think about this kind of from a more intuitive perspective. And so we are seeing what we expect, which is a lower P vaporization. I've also done this at a higher temperature. So P2, when we raise the temperature to 383 Kelvin, I'm apologizing, my handwriting is poor, but I'm working on it. that is equivalent to 110 degrees Celsius. So I increase the temperature of this water above its boiling point at normal conditions. And what we're finding is that we get a P vaporization of 1.41 atm. And so the reason why we're seeing this is that when I've given those water molecules even more internal energy by giving them a higher temperature, they're going to have even more excitement and encouragement to jump into that vapor phase. So if we want to keep them in that liquid phase, we're going to need to bump up the pressure to have more stuff pushing down on those water molecules. And that's why we need to have a higher pressure. That's the reason why our P vaporization is higher for water when we increase its temperature above its boiling point temperature under normal circumstances would be 1 atmosphere. So that is going to wrap things up for this video, but I hope this is helpful stuff. Thank you all for watching. Let me know if you have any questions, and I'll talk to you guys next time.